Okay, we're going to look at this idea of sum and product of the roots. Now, what we saw yesterday was sometimes the roots are imaginary, so they don't actually exist in the real number system. But that doesn't stop us using them. We don't actually need to know what alpha and beta are in order to add them together. Because if we know they're the roots of this particular equation, the general equation, then I know that ax squared plus bx plus c must be able to be factorised to be some multiple, a, times x minus alpha, x minus beta, because that would produce solutions, x equals alpha or x equals beta. If I expand the right hand side out and group things together, then I get a relationship between the coefficients of the equation and the roots. And we can say, well look, the sum of the roots is always going to be minus b on a. And the product of the roots is always going to be c on a. And again, this comes back to the idea of when we're factorising monics, so a is 1, we say what multiplies together to give the constant, what adds together to give the middle number. So it's all coming from the same idea. So if we have to find the quadratic, they've told us the two roots. And we looked at this idea before, but now I guess we can look at it in a more formal way. Well, I can say, well, look, I know the sum of the roots is -1. I know the product of the roots is -6. So therefore it must have come from a quadratic, x squared plus x minus 6. If I make it monic, so a is 1, then alpha beta must be c, and alpha plus beta must be negative b. Now that's useful when we get the roots not in nice rational numbers, but they will always appear, by the way, in conjugate pairs. So if they're not going to be a nice, neat, rational number like we've got here, 2 and -3, then the two solutions should be the conjugate of each other. And so in this case, 2 plus root 5 and 2 minus root 5. And so when we add them, the irrational part cancels out. So alpha plus beta is 4. And when we multiply them, it also gets rid of the irrationality, because we're saying difference of two squares. And so we square the square root of 5. So our equation for that one, x squared minus 4x minus 1. But we can have a lot more fun than that. So alpha and beta are the roots of this particular quadratic. To start off with, they usually ask the standard ones. Oh, well, what is alpha plus beta? Oh, that's minus b on a, so 3 on 2. What is alpha beta? Oh, well, c on a, minus 1/2. But then they ask us other ones. A real common one. What's alpha squared plus beta squared? Now, alpha squared plus beta squared will always be alpha plus beta all squared minus 2 alpha beta. Basically, it's the rearrangement of the perfect square. Because if I said to you, what was alpha plus beta all squared, you would say, oh, that's alpha squared plus 2 alpha beta plus beta squared. And you basically moved the 2 alpha beta to the other side. We've worked out alpha plus beta, and we've worked out alpha beta, so we can substitute in. And eventually working it out to be 13 on 4. So that relationship, as I say, it's a common sort of a question, alpha squared plus beta squared, and it's fine to just quote it. I mean, it's a standard sort of result. Now, this time, 1 on alpha plus 1 on beta, treat it like an algebraic fraction. We get a common denominator of alpha beta, which we've worked out, and then the numerator becomes alpha plus beta, which we've also worked out. So we can substitute in, the denominators cancel, we get -3 for an answer. Find the value of m. All they've told us is one root is double the other. So in that case, instead of saying the roots are alpha and beta, one root's the double of the other. So I'm going to say they're alpha and 2 alpha. So the sum of the roots, alpha plus 2 alpha, is -6. And the product of the roots, alpha times 2 alpha, is m. Remember, we're trying to find the value of m. But basically I've got simultaneous equations there. For the first one I can work out alpha is -2. I can substitute it into the second one, and eventually, there we go, m is 8. Find the value of m in this wonderful expression. one root is the reciprocal of the other. If I see that one, I'm going to play around with the product of the roots, because if one is the reciprocal of the other, then when they multiply together, they must give 1. So I'm going to call the roots alpha, and the other root is its reciprocal, so 1 on alpha. So the product of the roots, I don't actually need to know what alpha is, because alpha times 1 on alpha will be 1, and in our expression it's going to be 1 over 2m minus 1. We're trying to find m, so we just solve that little one, and we get m is 1. So I guess with each of them, it's a matter of defining what we know. Alpha plus beta, the common ones, but then sometimes we have to manipulate those to get the result that we're looking for.